Hello and welcome. I'm Rashid Bashir, Dean of the Grainger College of Engineering at the University of Illinois at Urbana-Champaign. Today, we have the distinct honor of celebrating our Grainger engineering legacy of innovation and societal transformation by commemorating the 75th anniversary of the transistor, invented by our very own two-time Nobel Prize winner, Professor John Bardeen. The world depends on Grainger engineers for world-shaking innovation, and Bardeen's transistor invention has certainly changed the world in more ways than we can count. Joining us today as we envision the future of the microelectronics and the semiconductor industries are three giants and friends of the Grainger College of Engineering who are leading a technological revolution that we're all experiencing globally. Arvind Krishna, IBM's chairman and CEO, is the architect of the strategy behind IBM's transformation into the world's leading hybrid cloud and AI company. Trained as an electrical engineer and earning his PhD right here at Illinois, Arvind began his career in IBM's research division, where he contributed to the development of the earliest wireless LAN systems. He went on to a variety of leadership roles that included overseeing IBM's Systems and Technology Group, the Global Research Division, and the cloud and cognitive software business. Under his leadership, today's IBM is applying these technologies to help organizations worldwide transform digitally, increase productivity, reduce costs, drive innovation, and fuel growth. Arvind is also a passionate advocate for policies that strengthen America's technology leadership, notably his outspoken support of the CHIPS Act that is once-in-a-generation investment in the US semiconductor industry. Please join me in welcoming one of the country's most dynamic technologists and business leaders, and a proud UIUC Grainger alum, Arvind Krishna. Next, I'll introduce Jensen Huang. He's president and CEO of NVIDIA. He founded the company nearly 30 years ago, making chips for video game machines. The company's pioneering work in accelerated computing extended its reach into professional graphics and scientific computing. Today, NVIDIA is the engine of AI. ChatGPT, powered by an NVIDIA AI supercomputer, has captured the world's imagination and has sparked the iPhone moment for AI. Jensen, one of the longest-standing founder CEOs in any industry, is the recipient of the 2004 Dr. Morris Chang Exemplary Leadership Award and the prestigious Robert N. Noyce Award. Fortune magazine named him its 2017 Business Person of the Year. Under Jensen's leadership, NVIDIA has become one of the most consequential companies in the history of computing. Please welcome Jensen Huang. And our third CEO, Pat Gelsinger, CEO of Intel Corporation, began his career at Intel, where he was appointed the company's youngest VP and was the architect of the original 486 processor. A few years later, he became Intel's first CTO. In 2008, Pat was named a fellow of the IEEE and awarded an honorary doctorate of letters in 2008 from William Jessup University. In 2020, he was appointed by the president to the National Security Telecommunications Advisory Committee. Before joining Intel in February 2021, Pat spent 9 years as CEO of VMware. In that role, he transformed VMware into a recognized global leader in cloud infrastructure, enterprise mobility, and cybersecurity, almost tripling the company's annual revenues. He was ranked the best CEO in America in 2019, according to an annual survey by Glassdoor. Please welcome Pat Gelsinger. And it is also my great pleasure to introduce another giant, our moderator for today's discussion, Ms. Penny Pritzker. Penny is a founder and chairman of the investment firm PSP Partners, former US Secretary of Commerce in the Obama administration, past member of PCAST, which is the President's Council of Advisors in Science and Technology, a board member for Microsoft, an investor in a number of other technology companies. For decades, Penny has been a national leader in advancing our national dialogue and strategy around science and technology, while at the same time working tirelessly to ensure that our workers have the support they need to adapt, adjust, and thrive. As Secretary of Commerce, Penny was always looking over the horizon. And as such, she and her team in 2015 created the task force and the subsequent report to President Obama, which laid the groundwork for the CHIPS Act. So we're really fortunate to have Penny with us today. In her role as one of the chairs of the Biden transition, Penny raised the pressing issue of semiconductors in her first meeting with top officials for then President-elect Biden. Along with Bruce Andrews, who was her Deputy Secretary of Commerce, who is now at Intel, Penny has worked tirelessly to elevate the urgency of our national security and economic prosperity as it relates to the semiconductor industry. And now Penny is a tremendous partner with us in the Grainger College of Engineering and the University of Illinois to train and retrain the talent that are needed for our future tech workforce. Our Midwest region, specifically Chicago, is a hotbed of innovation across multiple technology areas. And together with Penny and our numerous partners, we are convening our collective leadership to once again change the world. Now, please welcome Ms. Penny Pritzker.
Thank you so much, Rashid, for that very generous introduction. It is such a great pleasure to be with all of you today and to serve as your moderator for this conversation with such innovation luminaries, as we recognize the importance to our society and economy of the 75th anniversary of the transistor itself and discuss the future of microelectronics. As Rashid said, I am very proud of the part my team played at the Department of Commerce to lay the groundwork for what would become the CHIPS and Science Act. This law is groundbreaking in so many ways and will help ensure that the United States can remain the world's leader in innovation and discovery. I can't tell you how excited I am for today's conversation. We have three of the world's top leaders of technology companies who are on the front lines of turning research into viable technology products and services. And in the process, they are also creating jobs and opportunity for thousands and thousands of people. With that, I'm going to pose questions to our panelists and ask each of them to respond to each question. So without further ado, let's get started. So first, Pat, I'm going to begin with you, but I'm going to ask each of you after Pat responds to respond to the same question. The invention of the point contact transistor by Bardeen and Brattain and Shockley's subsequent junction transistor represented a turning point in electronic technology. Over the last 75 years, what has been the impact of transistor technology and its most important uses? Pat, I'll start with you.
Well, the basic idea of an on-off transistor, right, became, the basis for everything, and, as we look at computers, computer technology, digital everything, essentially everything is digital. Every aspect of human existence is becoming more digital. Everything digital runs on semiconductors and transistors. And, that basic on-off switch now, our biggest chip, if you look at our high-end HPC chip here, we have 100 billion transistors on here. Right, 100 billion, right, devices. We said by the end of the decade, we expect to put 1 trillion transistors into a package. So, it's not just the big for the highest performance computing, right? It's also the small, right? And we're seeing computers become part of every light switch, every thermostat, every other aspect of human existence. And, as the world becomes more and more digital, this basic idea, right, of a switch that we can now do at scale, right, is permeating every aspect of a human existence. And it's why we've put such emphasis, and I'm sure we'll touch on the CHIPS Act and other things as we go forward, where, the world geopolitic has been defined by where the oil reserves are for the last 5 decades. We would argue that where the technology supply chains are is more important for the next 5 decades. It literally has become the underlayment for all forms of human existence today, and even more so in the future.
Jensen, I'd love you to answer the same question if you don't mind.
First of all, I'm delighted to help celebrate the 75th birthday of the transistor. I'm almost as old. I think Pat is definitely old. Glad to be here. My career tracked the advance of one of the most impactful implications of the transistor is the formation of the computer industry. In the last 40 years, I've had the benefit of enjoying the transition from mini computers and workstations and client server systems to the personal computer revolution, to the internet computing revolution, to cloud computing, mobile computing, and now AI. Each and every one of these phase changes, these transitions in the computer industry wouldn't have been possible if not for the miniaturization of the transistor, if not for the fact that we could do so much more with the transistor, that we can express programming languages on top that made us more and more productive. Each one of the changes, each one of the platform changes or phase shifts in the computer industry enable us to express more productive applications more easily, and it enabled us to reach more people, and it created applications that were more magical each time. One simple example is during the times of the PC industry, there were probably tens of applications, hundreds of applications that represented the body of work of the industry. Today, on a mobile device, you have millions of applications. And now we're at the juncture of a new computing platform, a new type of computer where the programming language is not BASIC or Fortran or Pascal or C or C++ or Java. The programming language is just human language, your choice. Any language you choose, this computer will make its best attempt to try to understand you, and in fact, understands you quite well. You could have a computer now that you don't have to program, or you could tell the computer to go write you a program. This type of new computing paradigm is really quite extraordinary. And so it's fairly clear now that with the advance of the transistor, we are now upon a new industrial revolution, not the replication of or the automation of energy production, or the first one was food production, I guess, energy production or mechanical machinery production. This one is the production of intelligence. None of this would have been possible without the advances of computing, and none of it would have been possible without the invention of the transistor. And so the entire society is built upon this one incredible invention.
Thank you very much, Arvind.
Yeah, so let me build quickly on what both Pat and Jensen talked about, because I agree with all of that. So I'll take it in a slightly different dimension, which is the economic productivity. If you look at semiconductors over the last, let's call it 60 years, because it did take about 10 years to get to manufacturing, there is somewhere between 100,000 to 1 million times advantage in the production cost of these technologies over the last 60 years. So a lot of the benefits we're talking about are generated not just because of the technology, but also by how much more cheaper it is to get each unit of work out. It is perhaps, I think, it's the unique technology that has had anywhere near that kind of run. In most other technologies, you'd be ecstatic to get about 10, maybe 20 times at the most over their lifetimes. This one is at over 100,000, going to get to 1 million, and that is going to continue. I think that aspect of semiconductors is unique and is driven by the original inventions. And you can draw a straight arc from what Professor Bardeen did to what all of us are doing today on these cost curves. That cost enables all this work that both Pat and Jensen talked about.
Thank you. Jensen, what are some of the most important innovations in device and fabrication technologies that have occurred over the last 75 years?
Well, I was the first generation after the first career generation, I guess, generation of engineers after the integrated circuit. And so I had the benefit of enjoying integrated circuits. And since then, and when I first started my career, my first chip was designed by CMOS, TTL on the transceivers, I/O, and CMOS on the inside. So I had the benefit of enjoying CMOS, the first generation of engineers to enjoy CMOS. The MOSFET was a tremendous invention. And obviously, because it was such a, if you will, simple device back then, Carver Mead's theories and design methodologies, and Robert Dennard's theories about how to scale transistors, and all of that embodied within Gordon Moore's challenge and Gordon Moore's law of how transistors will continue to integrate into a monolithic device. That drove the industry tremendously. The invention of the FinFET by Chen-Mi Hu at Berkeley, very, very important invention that allows us to continue to scale. But one of the most important inventions, of course, is lithography. For us to be able to print and produce geometries and devices of finer and finer detail, which then, of course, our recent technologies with DUV and EUV, all of that made it possible for us to integrate such incredible complexity onto a single device. Those are probably some of the ones that come to mind that impacted the actual manufacturing and design of many of the chips that I worked on. And if not for those inventions, NVIDIA wouldn't be here today.
Arvind, I'd love your thoughts on this.
Look, I'm so happy to hear Jensen talk about some of the giants in the industry when he reeled off Gordon Moore and Dennard and many others. I think a few that I would talk about are the help behind both the speed and the scaling of these technologies. So when I think about the original materials, there was silicon, there was germanium, but then as you went along, you had to get more and more current and heat into and out of these devices. So I would say leveraging copper interconnects is one example, and that began a whole series of all kinds of materials entering the actual transistors and the integrated circuit. Another example that I'm really proud of is that the structure of the transistor itself is changing. Many of us think of these originally as two-dimensional devices, and now getting to gate all around, which I think is one, not the only, but one of the fundamentals that is helping us now scale to 2 nanometers and beyond, which will further help Jensen build even denser chips, I think, as we go, is another of those examples. And so sort of going to the third dimension as opposed to just in 2 dimensions and imagining what can happen is a fantastic one. I'll mention one final one and stop, which is the whole issue around memory and what is called non-volatile memory, and how much that has enabled different applications by bringing the sort of the semiconductor cost curve to permanent memory. What we all think of as sort of flash devices, to use that word, is another great example which has opened up lots of applications.
Thank you, Pat. We'd love your thoughts on this as well.
Yeah, and if you think about the 75 years since the transistor began, of the first 30 or so years, there was actually quite a lot of debate, on the material structure, that would end up becoming the one for the industry. Bipolar devices, silicon germanium, right? Indium phosphide. There was a lot of that, right? And then the world settled on silicon, right? And I will just say, silicon is God's gift to mankind, right? This massively manufacturable, stable, and right. I always joke today as we're, continuing the progression of Moore's law right now, just a few days after his passing, silicon has been this extraordinary structure, and there's not a lot of silicon left in silicon devices. It's a scaffolding that we've been able to bring more and more material science into, and now about, a quarter of the periodic table is used right in the manufacturing of a silicon chip. So it really has been the magical material that's shown to be manufacturable, scalable, right, resilient over a long period of time. The second major was the moving to CMOS, right, which is the fundamental transistor structure that we're using today. So these two have been the basis for essentially the last 2.5 decades, right, of transistor and device innovation. And picking up a little bit of Jensen's comments, as I say, we see our way clearly. And when we think about Moore's law, to me, we've been declaring the death of it for about 3 decades, and we keep finding innovations to move it forward. And the analogy I use would be is we always have about 10 years visibility, right? And when you've gone 5 more years, well, we have about 10 years of visibility. And so we've been able to keep pushing it forward over time. And today, we see 4 innovations that allow us to say, yep, we got about another decade of Moore's Law. One is EUV, right? As Jensen referenced, more than an order of magnitude improvement, to 13.5 nanometer light, from 193. So huge progress in lithography, which is the core of semiconductors. Second is we're now doing wafer on wafer. So we've been able to move power delivery to the backside, and for our next major process technology, solving many of the interconnect issues and power delivery challenges. Third, right, this gate all around transistor, as Arvind referenced, the next major transistor structure, from bulk to strained silicon to FinFET, and now gate all around. But the last one being 3D packaging. We're now innovating not just in Denard's, view of X, Y, but X, Y, and Z, right? And those 4 innovations, we think we're good for the next decade, right? And getting to the trillion transistor device around 2030. Innovation is alive and well. And, in honor of Gordon, we're not done yet.
Thank you. Thank you. Arvind, can you comment on what technologies are on the horizons from a materials and device perspective that are going to enable a continuous advancement of hardware functionality? Will the focus be on size and density in silicon, small transistors, and more per chip?
I think the rate and demand for getting smaller transistors that are less power hungry is always going to be there. We all want to, as I think Pat began by talking about, we're walking around with more compute in our pocket today, I think by an order of magnitude than was in the entire Apollo lunar program. So just to give people a sense, that is driven by miniaturization. I think that race is going to continue. It is not going to stop. If you just think about it, I think that both Pat and I talked about the gate all around. Those are going to enable another 90% reduction in power and another 90% increase in the kind of devices you can put down on one. I think that is one that is definite. But there is another dimension that is going to come, and this is going to sound funny. It is actually by using less precision, not by using more precision. And that is going to make a big difference to the kind of chips that both Jensen and Pat build in the areas of artificial intelligence. Being able to do things with less precision, leveraging more analog techniques, perhaps closer to the memory, is going to allow a lot more AI to happen in much smaller devices and much closer to the edge. That sort of lower precision and leveraging memory-based computing technologies and what is sometimes referred to as analog computing, though it's not quite accurate from a computer science view. And since this is an engineering audience, I'll say it's a very rough approximation, but it is going to enable a lot more in AI. And I can't help but also talk about one that is going to go the other way, larger devices that are going to be needed for quantum computing, something that the whole Illinois ecosystem is really strong on, from Chicago down to Urbana-Champaign. And I think that it's going to explore another set of materials that are actually very, very stable at temperatures in the millikelvin level that I'm also excited about that are coming into play that may make their way back to the other technologies, but are certainly going to be essential for quantum. So those 3, I think, are really big advances that are right. A couple are right there, and one of them around the memory is sort of maybe a couple of years away.
Pat?
Yeah, and building on a few of Arvind's comments, as I like to say, hey, we're just going to keep finding materials to put into the silicon structure. And, whether we're inventing new molecules, leveraging new portions of the periodic table, finding new effects, we're not done in that respect. And for instance, right now, a lot of intrigue going on in things like gallium nitride for higher power devices, silicon carbide devices for much higher power capabilities. Also at the other end of the spectrum is innovations that allow us to go to much lower voltages. Because essentially every aspect, and if we recall CV squared, voltage is a exponential function on power, right? Being able to move to lower power devices, and essentially everything is power limited, right? Across our spectrum. Data centers are now power limited. There are mobile devices, so innovations that allow us to go to lower and lower voltages will be crucial to our continuing innovation, whether that's for the biggest data centers that Jensen and I build or for the smallest mobile devices that we build. Everything is power limited. We'd also point to the work in quantum, and Arvind has one of the premier programs in quantum. I have one of the premier programs in quantum. We're building ours on silicon. So, I think we will be able to use God's magical material more effectively to scale them to, getting to million plus qubit devices over time. And we think that'll be, the next major breakthrough area, will be when we get to quantum supremacy, probably sometime around the end of the decade. So, plenty of areas of innovation and material science, manufacturing science, as well as system architectures. All of them have more opportunity in front of us.
Thank you. Jensen, love your thoughts on this as well.
Well, this is one of the most amazing industries in the world. In just about every single direction, every single dimension, we're pushing against the laws of physics. And yet, with cloud computing and artificial intelligence, we find ourselves needing to build more and more powerful computers at a time when we are power constrained. And almost in every single dimension that we push against, there's tremendous limits. Of course, there are many levers that we're taking advantage of. Artificial intelligence is fundamentally a statistical computing approach. And so quantization, numerical precision, as Arvind suggested, are levers that we can play against. On the other hand, in the final analysis, the amount of data that we have to compute and these large language models and the neural networks that we're trying to create are really, really large. And so we have to achieve over the course of the next 10 years, what I hope that we achieved in the last 10 years, which is approximately 1 million times scale up in the amount of computation that we did. 1 million times scale up during this time is really, really difficult. There are several areas that I'm hopeful for. One, computational lithography, I believe, will be able to allow us to bring artificial intelligence and software techniques to the manufacturing process in a much, much deeper way. And hopefully, between the work that we're doing with computational lithography and using software techniques and artificial intelligence techniques in combination with EUV, we could push further into device geometries. The breakthroughs with very low power, very energy efficient SerDes, so that we can take what is otherwise a chip that naturally wants to be one giant chip, we can break it up into a whole lot of smaller chips. The chiplet idea, the 3D packaging idea, is an area where computer architecture and computer design will be revolutionized. Whereas this is an invention that is actually very profound, that came out of Intel a long time ago, called PCI Express. PCI Express has been the fabric of computer system composition for a long time. We now have an opportunity with chiplets and 3D packaging and multi-die packaging and the creation of UCIe, basically PCI Express, except for chip to chip. We have the opportunity to do system composition and system design in a very, very different way. In combination with that, we still have to think of new ways to extract the power and cool the systems that used to be, a few hundred watts, but now will be measured in kilowatts, if not 100 kilowatts at a time. These systems are going to be insanely powerful, power hungry and powerful. And the density of computing is going to go through the roof. There's a lot of first principle physics work that many of the students of Illinois will have to endeavor, and And I look forward to all the great breakthroughs that will come from them.
Jensen, it's dangerous for me to jump in here among the three of you to comment, but I would say from where I sit on the board of Microsoft and I chair the Environmental, Social, and Public Policy Committee, which is an unusual type of committee on a public company. But we're very aware at Microsoft of our power usage in the United States. It's massive, and we take that along with, we made a commitment by 2030 to be carbon negative. And so the innovations that need to occur that you're talking about are absolutely essential. We can't really just keep consuming the amount of energy the way we have in the past. The architecture needs to evolve, and the materials need to evolve. And I'm way out of my depth in the science of that or the technology of it, but I totally appreciate what you've just said. Pat, turning over to you. In the 1980s, the United States manufactured 30% of the world's semiconductor chips. Today, that number is closer to 12%. What's it going to take to regain our position in this technology? And is the CHIPS Act enough to get us there? What will be the impact if the decline continues?
Yeah, as I indicated in my opening comments, I do believe this is a matter of, literally, the most important matter of our supply chains for the future. It's critical, right? Not just for our industry, for manufacturing, for the security of our technology future, national defense, et cetera. This is a vital topic. And obviously with the passage last year of the CHIPS Act, I would argue, and our companies represented here had strong roles in that. This was the most important piece of industrial policy legislation since World War II, right? It's that important to change the vector. And I do believe that the CHIPS Act was sort of the first domino in moving, us to begin rebuilding this manufacturing. It's 30 years that we essentially saw us go from 80-20 in Europe and US to 20-80, right? And we're not going to overnight reverse that trend, even though, the moonshot that I've challenged Gina Raimondo at Commerce today and Ursula von der Leyen, president of the EU, was in a decade, can we get to 50-50? Right, and that would be an extraordinary reversal. And since the CHIPS Act was signed and approved, we've seen major manufacturing commitments on U.S. soil by Micron, Samsung, TSMC, and two by Intel. Right, so we're starting to see some of those early signs. But we believe this is the first domino. We have to continue it, with earnestness, for the next several years to swing that, because there's strong motivations. The U.S. never took a vote saying, let's get rid of this industry. But the economies and the legislatures of Taiwan, of Korea, and most importantly, China voted to get this industry. So this was such an important milestone, but now we have to follow through. We have to have, commerce aggressively executed. I don't think Chip 1 is going to be adequate. We'll probably need a CHIPS 2. At some point, as part of the CHIPS and Science Act, CHIPS and science was also the many efforts around the science that goes behind it and the formation of the National Semiconductor Technology Center. We have to get back to building the future. And every time we start major new technologies on American soil, we lead in the building of those technologies for the future. And of course, there's numerous other aspects that are going to be required. One of the things, we have our shuttle program. I want every university in America to be running their shuttle programs, on the Intel foundry, right? That becomes the basis for every startup company in America. That becomes the basis for every national security project in America. This won't change overnight. It took 30 years for it to leave our shores, but hopefully in a decade, we can have substantively rebuilt what I think is the most vital manufacturing industry of tomorrow.
Thank you, Jensen.
The future of computing, and we established that computing is the fabric of society and the fabric of industry, the fabric of economy. And we spoke about the three dimensions already today, and there are three critical dimensions to advance the future. One, and all these three dimensions are exactly the same three dimensions, Penny, that will help us reduce the amount of power consumed to do computation by several orders of magnitude. The first dimension, of course, is the device physics, and there are tremendous opportunities still ahead, and the industry is pushing hard to achieve it. The second is how a computer is built. A computer was built as a personal computer for a while, is built as a phone for a while. Today, the computer is the data center. The data center is the computer. And we have to rethink how we architect the entire computer and recompose it in a way that enables us to save a great deal of power and achieve performance. And the third, and is a very important one, is the computing model. This is an area that we can be very, very hopeful for. And the reason for that is because we have tangible evidence that the computing model going from general purpose computing to accelerated computing and AI has an opportunity, has the ability, not just opportunity, the ability to reduce the amount of power used for any particular computation by many orders of magnitude. We've demonstrated the ability to do weather simulation by 10 to 50,000 times less energy. We've done that. We've demonstrated that in many, many areas. These three dimensions are vital to the future of computing. Now, speaking of the CHIP Act, it's incredibly important to manufacture in order to be good at something. Doing basic research is very important. Doing engineering is important, but manufacturing allows you to practice the art, to actually understand how to how to advance forward. The amount of manufacturing is a greater debate. What do you manufacture? How much do you manufacture is certainly up for greater debate. One area that I might suggest is, if I could use as an example, NVIDIA invented the GPU. And yet today, GPUs are available from just about every computer maker and every chip maker in the world. In some way of measuring the just the number of GPUs shipped in the world, NVIDIA's market share in GPUs is extremely low. And yet today, we still are able to advance the fundamental art of GPUs at world-leading capabilities. And that comes from the fact that we continue to do basic research, that we architect, that we design, but we also manufacture GPUs. We just don't need to manufacture all of the world's GPUs in order to be incredibly good at it. And so that is the question is, how much do we have to do? But we surely have to do so.
Thank you. Arvind?
I'm going to build on things that have been talked about earlier here. So if you look at any nation and any economy, everybody agreed hundreds of years ago that the financial system was critical to the safety of the economy. So people had central banks and they had currencies. I would hypothesize very few governments would be willing to outsource their central bank to some other place. The second one everybody agreed on about 100 years ago was energy. The nations which have been energy rich and energy sufficient, maybe not 100%, but close, have found that they can actually get through crises in a much easier way, like some of the current geopolitics. I think the world woke up to that technology, specifically semiconductor, is as important as those two, not getting to be, not close, as. So if you get there, then you say you've got to have sufficient capacity on both the dimensions that both Jensen and Pat talked about. You've got to have sufficient capacity. That doesn't mean 100%, but sufficient on manufacturing. And you've got to have the R&D capability to then push that manufacturing to be the most effective. And I would agree with Jensen. I think that today power consumption is probably the most critical, as long as you also advance computing on that same dimension. So that is one big set of attributes. That's why the CHIPS Act is so important. I would assert, however, you need a second dimension. Is it another CHIPS Act? Is it more R&D? I'm not so sure. I would assert, Penny, especially going back to some of your government days in public service, I think that government has to declare that they are not going to buy the lowest cost good, not private. We are all often willing to pay 10 or 20% more. Government has to agree not to buy the lowest price, but to buy something that is sourced in this country. Without that, those factories will not be as full as they could be. If you do that, I think you will drive a whole lot more capacity along with the second CHIPS Act. In effect, it is through how you procure than just through, lowest cost.
Absolutely. I think all of us have learned throughout our careers that low cost isn't always the most efficient or effective way to source a product of any sort. Jensen, I'm going to switch the topic a little bit. What do you envision for the future of talent needed in the semiconductor industry? And how do we train our workforce across community colleges, research universities, et cetera, so that making it more diverse and rich with opportunities for women and historically marginalized groups for everybody?
Well, the opportunity is for the future to bring in more diversity is surely greater. And there's a couple of reasons for that. There's no question that understanding the first principles of physics and deep physics expertise is still required in this industry. This is one of the most challenging technologically challenging, fundamental technology challenging industries of all. And so we're going to need deep physicists and people who are passionate about the physical sciences. However, we have an opportunity now with the advances in artificial intelligence and the capabilities of software to integrate software into the machinery, integrate artificial intelligence into the machinery and the manufacturing loop so that we can exceed what otherwise would appear to be the limits of physics. Let me give you one example. We're all enjoying video conferencing today, and video conferencing and communications has historically been expected to be limited by Shannon's law. The amount of information that we can communicate through any medium with a certain amount of bandwidth. And yet with artificial intelligence, we can now transmit way more information than what otherwise would have been predicted by Shannon's limits. And the reason for that is because we're communicating with human prior knowledge of something, and that using artificial intelligence, we can perceive the environment and transmit the perception and reconstruct the environment in a level that is unachievable with classical compression. Well, there are many different examples like this where artificial intelligence is now able to take us beyond what previously were expected to be physical limits. And I think that my hope is that we would apply artificial intelligence and software to the semiconductor field to achieve incredible results. Now, this expands the diversity of expertise, the diversity of backgrounds, expands semiconductor physics, semiconductor manufacturing into a world of a lot more backgrounds and expertise. And so I'm hoping that this will be a wonderful way for us to expand.
Terrific. Arvind, I'd love your thoughts on talent.
Look, I actually believe that the bulk of the world is in a demographic decline in terms of number of people. So I think as leaders, it is imperative that we tap into more and more diverse pools of talent. Otherwise, we're not going to have sufficient talent. I'm talking about birth rates, overall populations, people of working age. And you can see that, by the way, in the current macroeconomic numbers. People talk about uncertainty in the economy, but unemployment is at an all-time low. So I think there is facts to support sort of my thesis. So then how do we tap into these bigger pools? There are lots of people in disadvantaged communities. How can we get their talent up so they can fill some roles? Not all roles are going to need college degrees. Let me acknowledge, I love my degree from Illinois. I love the years I spent there. I wouldn't give that up for anything. But not all jobs that all of us have need those degrees. And so how do you tap into more people from other backgrounds to be able to do some of those jobs? In some cases, leveraging some of the technologies around AI that Jensen talked about to make the people more productive and more competent. Third, I think it's imperative that as we look upon all of the R&D centers that we do, how do we actually leverage those to train more people for the workforce? I'm thinking of some of the public centers. There's a great one in Albany in semiconductors, but there are others. Our research labs and R&D centers around the country. How do we leverage them as places where we can train more people from the community in the important skills that they will need to be able to participate in all that we talked about? I think those are really important programs. And one that I'm passionate about, I know Illinois has done a good job in this, but not every university, is also the gender diversity in the STEM fields, especially in engineering. It's a big gap, and we all collectively have to work to go close that gap. I see no reason, there is no attitude and there is no talent or aptitude gap, but there is some kind of social gap that is stopping it. So we all need to work collectively on it. So I'll say sort of those 3 points and pause.
Thank you, Pat. Love your thoughts here.
Yeah, this is a great topic. We could spend a few hours on this. When I as a farm boy from Pennsylvania, a community college graduate before going on to university, grad school, et cetera, as Arvind indicated, this is across the spectrums. And one of the things that excites me so much about, reshoring manufacturing to America is the fact that it's everything from very entry-level workers, all the way up through the highest end PhD. So I do think it really does attract the entirety. And when we had the opportunity with the president to announce the groundbreaking in Ohio, it was also that we announced the end of the Rust Belt and the beginning of the Silicon Heartland, right? Because it opened up an entire demographic that, for the most part, the coast have participated in technology boom, but not the center of the nation. Right. And with that, I think it is, how do we embrace across the nation, the activities? And it wasn't just, Urbana-Champaign, but Ohio State, Michigan, Purdue, and all the other schools coming together and saying, OK, we're going to start to train for this resurgence in semiconductor and forming at the community college level all the way up through the university and PhD level, right, of what it took to rebuild a semiconductor capable workforce for the future. And, we initiated a $100 million program, half by NSF, half by Intel, and those grants are now getting underway, as we're working to rebuild that workforce. And, again, as Arvind indicated, the technology industry has been terrible on gender diversity. We're about 25-ish%, which means we're using half the talent of the planet, right? Which, boy, these areas we have to make better. So we've said that, for our sites that we're starting in Ohio, we are going to hire to our gender and to our diversity characteristics on day one. Not that we're trying to fix it after the fact, right? And I think it takes these very explicit, objectives to go, address it. And then maybe one final comment, if the world wants to send us their best and the brightest, we should accept, right? We need immigration reform. Every higher degree that we offer should come stapled, with a green card. Right. We just want the best and brightest to come to the greatest place on earth to do innovation across the entire spectrum. So, to me, this is just something that, we have the opportunity, to change the arc of the workforce of the future. And this is our time, and building on the CHIPS Act momentum, I think we do have a unique moment in history that we get to change this arc for America.
So gentlemen, you know that this is an area that I'm massively passionate about, which is really our commitment to really, there is talent everywhere, but there's not opportunity provided everywhere. And I love listening to you talk about, your individual, both the broad need to make opportunity available across the spectrum, and that how technology can actually make that available more broadly, but also that each of your companies are committed to that concept, which is really terrific. So I want to end with a lightning round, and I'll start with you, Pat. And really, you all, the three of you, are such accomplished leaders in technology and innovation. What is your advice to Grainger students interested in the microelectronics industry?
Well, my advice overall, get mentors, people who help you, have audacious goals, pursue your passions. In the semiconductor industry, it is changing every day, and you just couldn't have an industry that's more exciting and more critical to the future of every human on the planet. Join us. We want the best and brightest.
Terrific. Jensen?
Every device physicist in the future have to remember that the computer of the past was a chip, but the computer of the future is a data center. They have to remember that understanding physics is important, but augmenting that with software and augmenting that with artificial intelligence and information and understanding is vital to our future.
Arvind?
Well, I would tell every student, leverage the capability you have around you. Take as broad a curriculum within engineering as you can, and take some classes that have absolute rigor. Leverage that learning, because then you learn how to learn for the rest of your career. The second one I would tell you, and most engineering students don't think about this, do learn how to communicate, whether it be written or whether it be oral. The effectiveness, once you have to lead people or just expound your own ideas, the impact of that would be incredible.
Well, I would say, to all the students, what incredible insights we've had here today, and what wise advice you were all just given. So let me close by saying I'm so grateful to participate in what has been an absolutely incredibly illuminating conversation with such distinguished technology leaders as Pat, Arvind, and Jensen. And of course, personally, I want to give a huge thank you to Rashid and all of your talented faculty and students, and the many others at the Grainger College of Engineering. This is a great community, and it's so important to have this kind of dialogue. And thank you for submitting terrific questions. The work that you're doing in helping build opportunity for thousands and thousands of people at the Grainger School is not only important for Illinois, but throughout the world. And the research and discoveries of Grainger engineers are making a reality, no doubt will change our world for the better. So I'm going to turn it back over to Rashid to close out our conversation, but I just want to say thank you for inviting us all to participate today.
Thank you, Penny, for leading that great discussion. It was so inspirational and so informative. So thank you again. And thank you, Arvind, Jensen, and Pat, for sharing your vision, your insights on these really important topics, and especially also your advice to our students. So on behalf of the Grainger College of Engineering at the University of Illinois, Urbana-Champaign, we're just so grateful for your wisdom, your leadership, and your partnership, and especially your time today. It's really amazing that all three of you were able to come together for this hour. I know that together we will continue to push forward and solve these grand challenges that you outlined that are ahead of us, and our workforce, our economy, and our society will be better for it.